So, here's a ramp, and there is a block sliding down this ramp. So, what we are trying to find is at what point the block pushes the spring so that there is zero velocity. Here, it is frictionless, and here, there is friction.
So I'm going to do the math for this equation, or explain the math. So first we have to define the total energy of the equation. So the energy is going to be different in three places. Here we're going to have all potential energy. Here we're going to have 100% kinetic energy. And then here we're going to have 100% potential energy, which means there's going to be no movement here. Anyway, so the problem is when we find energy here, it's going to be the same here as it is here, but after it goes through the friction area, the block's going to lose velocity and therefore lose energy. So when it gets to this point, it's going to have less energy than it did up here. So we need to find the energy here, and then find how it changes, and then plug it into equation to find the potential energy, or potential spring energy, which will also give us change in x. So what we did was, first we found the potential energy at the beginning of the ramp, which we have a smaller drawing here. So we plugged into the potential energy equation, and we got this number. And what we did, so this is the potential energy, but it's also the total energy, because here is all potential energy, which means the total energy is going to be equal here, and this is all kinetic energy. So we plugged this number in to the kinetic equation, the kinetic energy equation, which gave us, and then we also plugged in mass for it. So we have velocity unsolved for. So we solve for velocity, and now we know how fast it's going at this point. And so we need velocity to find how much energy is lost in this area. So to find how much energy is lost in this area, here we have a free body diagram of the block in this area. And so we have the the force by weight, and then the force by the ground up. And since we have mu, we know the frictional force that way is. So we plugged it in, or we did the equation, and so now we have the frictional force going this way. And since there's nothing pushing on the weight this way, we know that that is the total force on the block in this area. So we plugged into the force equals mass times acceleration equation, and we plugged everything in, and acceleration is unsolved for, and we need acceleration. So we solved for acceleration, and it's 2.1 meters per second in this direction, away from acceleration, or away from the velocity. So to find how much velocity is lost in this area, we need to know how long it takes the block to travel, 7.5 meters. And this took a bit of work, but it's pretty simple. We just plugged into the kinematic equation, which you plug it where you have the factors change in x, which is 7.5, 1/2 times acceleration, which is this. But this is going to be a negative number because the acceleration is going opposite of the change in x and velocity. So we can leave velocity and change in x as positive, but acceleration is negative. And then, so velocity, for velocity, this is initial velocity, which means velocity at this point. So we plugged in the velocity we found here earlier. And so now we have everything for the equation except for t. So we solve for t using the quadratic formula. And when we use the quadratic formula, we got two answers, which are 10.126 seconds and 1.41 seconds. So if we think about what we plugged into the equation, there's going to be a constant force going this way, which means what the kinematic equation is telling us is that it's going to go here past this point at 1.48 seconds, 1.481 seconds, and then come back as it loses and gains velocity in this direction, since there's going to be a constant force according to this equation. So it's the bigger number is just it coming back in what you put in the equation, but we can ignore that, and so the number we want is this one. So that tells us how long it takes to cover this area with this negative acceleration. So knowing that, we can find the final velocity here. So we plugged in the initial velocity minus time times acceleration, which is the change in velocity, and so that will give us our final velocity, which is here. Now, the final velocity we need to plug into the kinetic energy equation, which is this. So we plugged it in for kinetic energy equals 1/2 mass times the velocity squared, and so we plugged that all in, and we found kinetic energy here. So this is the total energy of the equation right here, and you can see it's significantly less than it was up here, which is because it lost energy with the friction here. So now we have total energy right before it hits the spring. So this is 100% of energy here. So once it gets to this point, all kinetic energy will be transferred into potential spring energy. So we plugged that in. We plugged in this number for the total spring potential energy times 1/2 the spring coefficient, which they gave us here, which is 1,194 newtons per meter, times x squared. And x is going to be the change in x, because that's what we have. And so it's change in x squared, which is equal to x. So for this whole equation, we solved for x, and we got 3.1339 meters, which is how far it went. So, yay, done.
Oh my god.